In this lesson, we're going to start analyzing functions in a slightly different way. We've been looking at limits and how we can use those to analyze asymptotes and what happens at the end of our functions as an end behavior. Today we want to see what happens in between those things. In particular, we want to use our idea of a derivative, which tells us the slope or rate of change at any point, to help us figure out if functions are increasing or decreasing. We know that we can optimize a problem, that is, find the highest, lowest, max, min, where our tangent is a flat line. In other words, where our derivative is 0. If we look to the left or right of those points, we can often figure out our functions increasing to a maximum and then decreasing, or are they decreasing and then increasing. And we call these points turning points or stationary points, maximums and minimums. And one of the best tools for this is actually using a sign diagram, kind of like we did in higher functions, but with a slight difference to it. So we're going to start with a basic one, idea of a parabola, and show you how this idea is going to work. So we know this equation. We know that's a parabola. And we know a picture kind of looks like this. But what if we had a function where we didn't know the picture? If we didn't know there was a minimum at 0, 0, how could we use calculus to help us figure that out? Well, if we take our derivative, which in this case is 2x, and we set it equal to 0, we will find the optimal points of that function, as in the mins or the maxes. So we're going to solve this and find out that at 0, something strange is happening. Now we know from the picture that it's a minimum, but I don't want to use the picture. I want to use calculus. How can I do that? Well, we're going to make a sign diagram using the critical value of 0. And I want to see what happens to the left of 0, so in other words below 0, and to the right of 0. And using my derivative in these intervals, I can figure out if my function's increasing or decreasing. How do I do that? Well, let's pick a number that's less than 0, for instance, -1, and put it into our derivative. What do we get? Well, 2 times -1 is -2, and the key there is the fact that it's negative. If I pick another number in the other interval, let's try this one, let's say +1, and again put it into my derivative, I end up with +2. Key there again is the sign, it's positive. What does that tell me? Well, that tells me that this function is decreasing when I'm less than 0 and increasing when I'm greater than 0. If I were to draw that, it's going down and then it's going up. Well, doesn't that kind of look like a parabola? In particular, doesn't it tell us that we have a minimum right there? That's kind of handy. That's kind of how calculus is going to allow us to figure out maximums and minimums and other things about functions. So just the theory part. We call this our first derivative test. So if you make yourself a sign diagram, like we just did a second ago, and you might have more intervals than we had. We only had 2 there. We have lots of intervals. The signs that you get will tell you the kind of stationary or turning point that you've developed. Okay, if our derivative changes from a positive to a negative, it goes up and then down. It must have been a max. If it goes down and then up, it must have been a min. And if you get a sign diagram that has the same signs in it, as in a positive followed by a more positive thing, we call that an inflection point. A point where it goes flat for just a second. And the same could be true of a negative followed by a negative. A flat point just for a second. And those are the 3 different types of sign diagrams you can have, and the 3 different kinds of stationary or turning points that you can have. Let's try some. So using our first derivative, let's find the critical values and then complete an interval chart to figure out increasing or decreasing and figure out the extreme values. So my derivative, 3x squared minus 27, I want to set it equal to 0 because that would tell me where I go the flat spots. So we'll factor this just like we would with a quadratic. We'll solve it just like we did with the quadratic. So difference of squares. And my zeros will be x equals 3 and x equals -3. So I go to my interval table now. I always start with the leftmost 0, which is -3. I go from there to the next leftmost 0, which is +3. I always finish with the rightmost 0, so greater than 3. Remember, we want to talk about our derivative. We want to look for its signs. So if we pick a number less than -3, I'm just going to erase these arrows for a second here. Let's say, for instance, -4. If I put -4 in for my x's, I'll get 3 times -7 times -1. I don't really care what the number is, I care what its sign is. And that sign would be a positive, and it'd be a 21. If we do the same thing, we'll get rid of these numbers. Pick a number between -3 and +3. Let's try 0. That's a nice number. We'll get 3 times -3 times +3, which is a negative 27. So we don't care what the number, just a negative sign. And again, pick a number greater than 3. Let's try the number 4. Put that in, we'll get 3 times 1 times 7. And that's a positive number. So what have I seen here? I can tell you for sure that my function is increasing when an x is less than -3 and x is greater than +3, and it's decreasing when we're between those points. Now notice I didn't put any equal signs in here because at 3 and -3, we're changing direction. How are we changing? Well, let's draw it out. It goes up and then down. It goes down, then up. So obviously this one's a minimum and this one's a maximum. What are the values? -3 and something and +3 and something. If I want to know the something, the point that goes along with it, I have to go back to my original equation, because that's how we get points, and sub in -3 and +3. So for instance, we'll do the -3 one. We'll get -3 cubed minus 27 times -3 minus 10. You can punch that all into your calculator just the way it looks, and you should get 44. So I have a max at -3 and 44. If I do the same thing, but I use the +3 version, and the same procedure, I will get -64. And there's our stationary or turning points and their types. Okay, and we did that all with calculus. No picture necessary, no graphing technology necessary, just using the idea of rates of change. Okay, you guys are going to try the second one. Same ideas, slightly different function. Can you find me the turning points where it increases and decreases using calculus? So start off with your derivative. 12x cubed plus 12x squared minus 24x. Set it equal to 0. I want to know where the flat spots happen. We can factor this, so we might as well do both at the same time. Okay. I end up with a trinomial inside my bracket, so x plus 2 and x minus 1. There's the simple factors. We have 3 zeros. We've got 1 at 0. We've got 1 at -2. Oops, -2. And we've got 1 at 1. We can make our sign diagram starting with the furthest leftmost 0, which in this case is -2. And then we'll go between that one and the next leftmost 0, which is 0. And the next one, and then say greater than 1. Our whole idea is to use our derivative to figure out our rate of change. So on my sign table, I say derivative over here. And then I start picking numbers. So if x is -3, just going to erase the arrows so I can put numbers underneath it to think about this. If x was -3, we'd have -36. We'd have -1. We'd have -4. 3 negatives makes a negative. If we try the next one, let's try the number -1 in that interval. We'd have -12. We'd have +1. We'd have -2. 2 negatives make a positive. The next interval is very small, but we can choose decimals. Nothing wrong with that. Let's try the number 0.5. And the first one I get 6. I get 2.5. And I get -0.5. Well, 1 negative makes a negative. And if I try the last one, let's pick the number 2, let's say. We'd end up with 24, 4, and 1. And I have all positives, so I have a positive answer. So what can we say about this function? We can say we know where it's increasing. It's increasing when x is between 0 and -2, and also when x is greater than 1. and we could say it's decreasing at the other spots, the negative spots. So less than -2 and between 0 and 1. If we draw our picture, it goes down then up then down, down then up. So we know what kind of values we have at these points. We've got a min at -2 and something, a max at 0 and something, and a min at 1 and something. To get the somethings, go back to your equation. Now, I'm going to start with the easy one. Let's start with the 0 point. Sorry, the 0 point. If I put 0 in for all my x's, okay, I end up with 0. So that's a nice one, okay, 0, 0. If I put -2 in for my x's, we'll get 3 times -2 to the 4 plus 4 times -2 to the 3 minus 12 times -2 squared. We punch all that into our calculator and we get -32. Okay, so that's my min value here, right? -32. If we do the same thing but get the 1 in there, we'll have 3 times 1 to the 4, which is just 3, plus 4 times 1 to the 3, which is just 4, minus 12 times 1 squared. So in other words, we get 3 plus 4 minus 12, or -5. And there's our 3 turning points, our stationary points, again with just calculus. Now, I don't think the integral tables are that difficult to deal with, but some people find that, well, it's a lot of parts and pieces to keep track of. So let's move to the second derivative test. This is kind of a shortcut for figuring out mins or maxes. The first derivative tells us where they occur. The second derivative will actually tell you what kind they are. Okay, so we do the process where we take our derivative, say equal to 0, find your x's. If you then take those x's and put them into your second derivative, the sign of that answer will tell you it's a min or max. And here's the 3 rules. Rule 1, if your second derivative comes out to a positive, it's a minimum. If it comes out to a negative, it's a maximum. And if it comes out to 0, you're kind of in trouble. The test fails, and you have to use an interval table. Odds are there that it's an inflection point, but you don't know if it's an increasing or decreasing inflection point. So that's kind of why you need the table. Okay, so I'll give you an example of how one of these works. Okay, so we're no longer going to make tables. We're just going to make first and second derivatives. So we'll start off with our first derivative. Same old thing we've always done. So derivative of 6x squared minus 24. We want to make it equal 0, and then we can factor what's left over. Okay, this is the difference of squares, so x minus 2 and x plus 2. So in other words, at 2, there's something going on here. That's maybe a minimum, might be a maximum. Don't know what yet, and I don't want to make the table. So I go to my second derivative, which is the derivative of our first derivative, right? In this case, it's just the numbers 12x. I now check my critical points in the second derivative. So the first one was, let's see what happens at 2. That's 12 times 2, which is key here, positive 24. What does that tell me? The fact that it's a positive tells me it's a minimum. A minimum at 2 and something. How do I get the somethings? I go back to our original equation. That's one at the top here, and I plug in 2 for all the x's. F at 2, if you plug that in there, all the x's, you end up with -22. Okay, so we have a min at 2 and -22. If we do the same thing at the other critical point at -2, we end up with -24. What does that tell me? It tells me there's a max, because it's a negative. Where's the location of the max? -2 and, go back to the original equation. Okay, use it for finding points. Let's see what happens at -2. If we put in for all the x's, we end up with 42. So in other words, there's a max at -2 and 42. So now, based on this, I can get myself a rough sketch. And I say rough because I'm not really worried about the y-intercept and the x-intercept, and we'll do all that stuff later. I'm just worried about the shape of our graph for today. Okay, so what do I get? I know at 2 and -22, there's a min. And -2 and 42, there's a max. And the only way that happens is if I go up and down and back up again. And there's a rough sketch. And that's all we care about today is a rough sketch of what this function is going to look like. Okay? Like, if I can make it, I suppose, slightly nicer. If I fix the y-intercept, we know it's at 10. And that's a pretty obvious one. We can do that. But I'm not really worried about finding the zeros and finding anything else at this point, okay? Just the fact that where our mins and maxes happen to fall. I'll make better sketches down the road. Okay, you guys can try B. Same ideas. Use your first and second derivatives to figure out your mins and maxes. And then from there, make yourself a rough sketch. Okay, so first derivative, 4 times 1/4 just makes 1. So 1x cubed minus 6x squared. Set it equal to 0 and factor it. So we'll get x minus 6. We've got zeros at 0 and 6. Okay, second derivative. We get 3x squared minus 12x. Let's figure out what happens at 0. That's a nice one. 0. Oh no, we got 0. What does that tell me? This test just failed. I don't have a choice. I have to use an interval table. There's something weird going on here. Okay, so we call this a failed test. Okay, so let's go to the interval table. We don't have a choice this time. Leftmost 0 is 0. From 0 to 6, and greater than 6. Okay, we're back to our first derivative here. We want to see about our signs. So let's check our first derivative for signs. Let's pick a number less than 0. So instance, -1. -1 squared would make a positive, and -1 minus 6 is -7. Gives me a negative. Pick the number 1. 1 squared is a positive, but 1 minus 6 is a negative. Oh, there's why our test failed, right? We had two signs side by side that are the same. If you try the other one, try a number bigger than 6, let's pick the number 7, and we would have got positive 49 and positive 1, and that makes a positive. Now you could have used your second derivative test on the number 6. If we had tried that, f double prime at 6, we would have got 3 times 6 squared minus 12 times 6, which is 108 minus 72, which is 36. So that would have told us we would have had a min. Now our interval table tells us exactly the same information, right? That goes down and then back up again. So sure enough, we do have a min. But it would not have told us that about the inflection point. That's where our test failed. So our inflection point tells us it's going to go down, flat, and continue down. So we've got ourselves an inflection right here. And if I want to figure out the coordinates of those, right, we've got min at 6, inflection at 0. We go back to our original equation. If I put 0 in there, that's kind of nice, right? We get 0 minus 0, which is 0. And if we put 6 back into our original equation, 1/4 times 6 to the 4 minus 2 times 6 cubed. If we put 6 in there, you should end up with, I believe, -108. -108. So, if we're drawing ourselves a picture, again, just a rough sketch, because our numbers are pretty big, I've got an inflection point at 0, 0. That's 6, -108. Let's call that down there. Just a rough sketch. We don't even have a sense of scale in here, okay? All I know is that I have a down inflection point, so it's going to go down, flat, and then a minimum. And I know this end goes up somehow. When we have to make real sketches, when we're asked to graph something, we'll be more particular. But for now, a rough sketch is good enough. Okay? So that's how our second derivative test kind of works. It can shortcut the table idea unless it comes out to 0, like it did in that case. Okay, last one. Find me the greatest and least values for this function on this domain. So that's what we've been doing, right? Let's give it a try. So my greatest and least are mins and maxes. I can find that by using my derivative. 8x minus 3x squared. Make it equal 0. Factor this. So this is an ugly, messy one because it doesn't common factor very nicely except for the x. That's a little tricky to figure out the zeros, so let's solve it for the zeros. So we know the zeros are what makes something equal 0. So there's my two zeros. I want to know mins and maxes. Now, I don't know which one's which, but I know my second derivative test will tell me that. So let's move to our second derivative. We'll get 8 minus 6x. Let's try a second derivative at our critical values. We'll get 0 in there. We get 8. It's a positive 8, which tells me min. If I try the same thing at 8 thirds, we'll get 8 minus 6 times 8 thirds. We end up with 8 minus, what's that, 16? Or negative 8, which tells me, oh, it's a max there. It's a negative. Negative means max in this one case. Okay, so our min happens at 0. Our max happens at 8 thirds. If I want to know the points, I go back to my equation, right? So let's see what happens f at 0 and f at 8 thirds. So we put 0 into this original equation. That's a nice one. We get 0 minus 0, in other words, just 0. The next one, not so nice because we've got the messy fraction to deal with. So 4 times 8 thirds squared and minus 8 thirds cubed. Now, unfortunately, because this is a really messy decimal, or sorry, fraction, we'll have to turn to a decimal, and I get approximately 9.48. Okay, so we're thinking, that's my hint there, that we have a min at 0, 0, and a max at 8 thirds and 9.48. But there's one more piece of information this question gave us, or asked us about. It said find the greatest in these values of the function on this domain. And the fact that they're limiting us in a domain means something could happen in those endpoints. We don't know what happens at the edges of this function. So we need to figure that out. We need to figure out what's happening at the endpoints, -2 and 3. Because our function might go, what do we have? We have a min at 0, 0. Here, let me graph. 0, 0, and the max at here. But what if it goes down and goes up? Well, those points here and here might be higher or lower than our mins and our maxes. So we actually have to figure out always what happens at endpoints if we're given them. So we're going to use our original equation because it gives us points. And we're going to put -2 in. So 4 times -2 squared minus -2 cubed. We're going to do the same thing for 3. So 4 times 3 squared minus 3 cubed. And we're going to figure out both our values. So punch those into your calculator, and you should end up with 24 for the first one, I think, and 9 for the second. Okay, so what does that tell us? Well, if we look at it, the point -224 is actually higher than this max, okay? Which makes this, you might remember the words from last year, a local maximum. But for our cases, this is actually the highest, because 24 is bigger than 9.48. In terms of a minimum, I had, if you compare, oops, no, not 0, 0. If I compare all my 4 values here, I had 0, 0 and 3, 9. Well, definitely 0, 0 is lower than 3, 9. So this one is my lowest. Okay? It's not only the local min or max, it's actually the absolute min for this question for our purposes. Okay, based on the domain that we were given. Obviously this graph, if we actually went further left and further right, it's a cubic function, and cubic functions go up forever and down forever, but on our domain, the lowest we ever got to was at 0, 0. Okay, so just be careful when you get a defined domain. You can find your local things using your derivatives, your calculus ideas, but you might have extreme values on either endpoint, which you have to find just using our basic function. That's the end of this lesson. Try some of the homework. If you're stuck, we can chat about it.